Our packets are scrambled, so if somebody intercepts them, they can't understand what they are. And if an attacker tries to send information into our location, they don't have the key to scramble it so that when the VPN hardware unscrambles it, it means anything. So this gives us security. But it gives us secure communications over an unreliable network. There are still no guarantees as to whether your stuff is going to actually get there, not when or how often. Nothing. Zero. No QoS guarantees. But it's free. If we want to deal with the security question and the quality of service question, then we could start taking a look at IP VPN services from telecommunications carriers. This is essentially the same story as far as technology goes as the previous one, except that the network is providing the VPN hardware. And since the network is providing the VPN hardware, you have to pay to connect to this and pay to establish tunnels across it. And since you have to pay, this is not the internet. This is a very carefully controlled IP network that only carries traffic for which people are paying. So this is, if you want to think of it, a commercial IP network or a managed IP network. This has some strong advantages because if you sign up with a big carrier who's actually deployed points of presence in this VPN hardware in all of the cities that you need to go to, then they've spent all the capital cost to deploy the actual physical connections. You get secure communications between all of your locations. And since they're controlling the traffic that's flowing over this IP network, then we can do some quality of service guarantees, or at least start talking about them anyway. So this would probably be one of the first ways we would actually look at doing voice over IP over a wide area network, is to use a commercial IP service, a managed IP service. The side of this, well, what happens if they don't actually have points of presence everywhere you need to go to? That would be a problem. Another one is that this process of taking a packet, scrambling it, sending it across the IP network and unscrambling it, that introduces a delay. And all of this stuff was designed for data communications where delays don't really matter very much. They were not designed for voice over IP where delays are very important. What we might find is that the process of encryption and decryption adds in enough delay to blow our delay budget from the last discussion. So this is something we would have to take a close look at. And you can start thinking about all of the different things you're going to have to take into consideration when designing end-to-end voice over IP. This is where we're headed with this story. We like to call this a native voice over IP carrier because this is a telecommunications service provider that's gone to the expense to deploy an IP network that will handle both voice and data with expensive network equipment and lots of underlying horsepower connecting this equipment together, so that they can guarantee the end-to-end delays across the wide area network. So therefore we can start having some expectations as to what the quality of the reconstructed speech is going to be. There are many different elements on this diagram. If we start at the left, we've got a residence, and they've got an integrated access device connecting both their plain ordinary telephone service and their desktop home PC to a DSL or cable modem to connect onto the carrier. On the right side at the top, we've got a business, so they've got desktop PCs and servers, and they would have telephones on there as well, all connected together with a LAN. and then they've got a high-speed connection to the internet. And when we're talking about high speed for businesses going forward, we're talking about fiber access. Forget this copper wire cable modem DSL business. I want a fiber. And today you can get 10 megabit per second Ethernet over fiber, and gigabit per second Ethernet over fiber exists. Gigabit Ethernet over fiber is going to become ubiquitous going forward. That's what high speed is going to be 5 years from now. On the right side at the bottom, you see that there's a DS3 link from a gateway to an icon of a switch that has LEC IXC circuit switched PSTN, and then a telephone supporting plain ordinary telephone service connected to it. This is illustrating the idea that not everybody on the planet is going to have voice over IP. So even if you have voice over IP service, if you want to call somebody who doesn't, we have to be able to convert the phone call into traditional telephony. That takes a gateway. And then we have to hand the phone call off to possibly an inter-exchange carrier, but certainly a local exchange carrier, to terminate the phone call at the far end. So the interconnection between the native voice over IP carrier and the traditional network is going to be channels of streaming digitized speech, DS0s. These are measured in DS3s. A DS3 is 28 times 24 DS0 channels. That's what phone companies use to connect back and forth. At the top of the cloud is a connection that says LEC, IXC, Internet, VoIP, and DOIP networks. VoIP, of course, is voice over IP. DOIP, well, that's data over IP, in other words, the stuff we're doing already. And the connection there is a lambda on top of a little line going into an IP router. What we mean by lambda is that this is a wavelength. And anybody who has watched Fundamentals of Telecom 2 video will know what I'm talking about. This has to do with transmission technology and a particular technology called dense wave division multiplexing, where essentially we can put many different lasers, each at a different color of light, a different wavelength, on the same fiber. And so then we have the capability of moving hundreds, and in the future thousands, of SONET OC48 and OC192 connections over a single piece of glass thinner than one of your hairs. So what we're going to be doing in the future to connect IP networks together is we'll just have a router that can handle a whole wavelength, and we'll just have the fiber come in and then a splitter to split off that wavelength and plug it into the router, and we'll just connect routers together with wavelengths. In other words, connect them together at OC192. That's 10 gigabits per second. You think we've got high-speed communications now? You ain't seen nothing yet. In the middle of the picture, inside the cloud, and the cloud, of course, is the network infrastructure that this service provider has put in place. We've got the IP routers connected together with high capacity circuits, and that's what they're selling, is access to that. We have a gateway to be able to connect to the public switch telephone network, and in addition there's a little icon of a server. This server would be a number of computers that are running applications. Some of the applications they'll run, well, gatekeeper services, because this will be provided as a network service. You won't have to have your own gatekeeper to do the registration, admission, status, and call setup and signaling. They will provide that as a network service. And of course, you can think of all of the other value-added call management features that are going to be offered. Integrated messaging with voicemail and email. We've got caller ID on the web, and call disposition and profiling. The list goes on. And all of these things will be value-added services. This is where they're going to make all of their money. All carriers will be deploying networks that look like this. Some of them have already done it. T-Systems, a sister company to T-Mobile, they've got a global voice over IP native network. The cable companies have all said they're going to, so the phone companies will all have to as well.